Hello, this is Professor Chen, Mechanical Engineering. Today we're going to give you the head up about Chapter 2. Chapter 2 is to talk about our very first loading type we call the axial loading. And in this 5-minute head up, I will try to give you the big pictures, not to go into details, but hopefully from here you can find a good roadmap for your study. The axial loadings basically is this. We consider a material model, and this is called a bar. And under the loading, which loading is through these longitudinal directions, this is we call the axial loading. And for example, another example of axial loading can be this. If you consider this kind of square or kind of little bit fat material, then this can be also one example of the axial loading. In this case, this loading is acting in the x direction, for example, horizontal directions here. In this axial loading, actually we're going to we're going to study the deformations, which means how the material is deformed. And then from there, we're going to define a new term we call the strain. And from here, we're going to review Hooke's law. And this is a very important thing. From Hooke's law there, we're going to derive a few new concepts to students who are in this class. So we start from this picture here. So let me say this is a loading F. And say initial dimension here in the direction of the loading, let me call L0. So after loadings, we expect this material going to deform. By that much, and here I exaggerate the situations. So after loading, this material will be deformed because each material we call the elastic material. Okay, due to elasticity, material will deform, and just like the rubber band, you can see. And let me call this deformation. This is called the deformation. So here we introduce the concept of deformation. Let me call deformation is called delta. So now I'm going to introduce strain. So because this force is the normal force, so the normal force will induce the normal stress, and which has been discussed in chapter 1, and that also will induce the strain, and we call the normal strain, and that is we're going to define here. And normal strain we're using epsilon. By definition is divide the deformation delta by this original length. That's it. And because this has the unit of length, this has a unit of length. Basically, the strain has no unit, or we call the unitless, dimensionless. Okay, so now we have the define the stress and define the strain. And this material actually is under the mechanical loading in certain stretching machine. So during the loading situations, and here we can record by software of the machine, and we put the strain in the horizontal directions, we put the stress in the vertical directions. And in reality, you will see in the testing, the curve will look like this until it's broke. Until at this point, basically material break into two parts. Okay, and initially the material is under the normal loading. Okay, so this one is we call the rupture. And in certain domain here, in particular, I want to highlight in this range, this is a strain line. For all the natural material at the initial range of the epsilon, this is always strain line. And that is a very specific material properties. And because of the straight characteristics, we can use the geometry, and here we define the slope, and here using the symbol is what we call the E. So basically, we can write the sigma equal to E times epsilon, and this straight line happened in, we call this range is called the elastic regime. Elastic regime is this, something like this. We applied loadings, and then if we apply loading that happen in this range here, once we release the loading, the material will recover back to its original shape. So that's what we call the elastic range. And that is this, in this range, we categorize the stress to strain by this relation, and E representing is a slope of this curve. In particular, here we give the E a name. It's called the Young's modulus. This is the very first material properties you're going to learn in these chapters in ES 331. And this is called Hooke's law. And Hooke's law defines the response of the material to loading. And this is a deformation related quantity. This is a force related quantity. So that in similar way in your high school, Hooke's law basically is similar to F equal to K times delta. Delta is the spring deformations. F is the loading. K is the spring constant, just like this. Okay. And let me write it up here. Hooke's law is F equal to K delta. Okay. So that is your high school physics we know. So if you compare this one to here, you can see the similarity here. So in the first the portion of the chapter 2, we define this one, and you're going to exercise and how to calculate the stress and how to calculate the strain for different and various types of the bars. And that means the various is this. The bar could be like this shape, irregular, or bar can be composed by these kind of cross sections, or even more complicated, but basically the concept is from here. You calculate the strain, you calculate the stress, and use Hooke's law to relate the two response here.